Okay. A little piece of vocabulary. Syntax is the technical term for the form of a program, what a program looks like. So scheme syntax is open parenthesis, procedure, argument, 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 close parenthesis. That's what a function call looks like. Semantics is what that thing means. So open parenthesis, blah, blah, blah. What that means is call this procedure with these argument values after you've recursively evaluated the argument expressions. Okay? So if you look deep enough, programming languages, I was about to say all programming languages have the same semantics. That's clearly not true. Some programming languages, for example, are in normal order. I mean, real programming languages that people use. Some of them are like that. But more or less, you're going to see the same kinds of things in the semantics of every language. You're going to see some way to make a conditional decision, something like if or cond. You're going to see some way to have a loop, like a tail call. You're going to see some way to call functions. You're going to see some way to define variables. You know, all of those things, they're the same kinds of categories of meaning. The syntax of different programming languages is very, very different from each other. If you've studied another programming language, you'll know that. But you know, if you studied Java in high school or community college or C++ or something, that looks much more different from Scheme than the meaning is different from Scheme. Okay? So syntax and semantics, piece of vocabulary there. Big important point. We are here dealing with two different programming languages. Okay, the calculator is a program written in Scheme. The language that the calculator implements is a programming language, a really trivial one, but a programming language, that isn't Scheme. Okay? So when I say, for example, that there are no variables in the calculator language, right? So if I say, you know, foo, that's an error. If I say plus sign, now let's be clear about this. If I say plus sign in parentheses, that's 0. If I just say plus sign, that's an error. The error message is bad expression, plus sign. Okay? That wouldn't be true in STK. If I say plus sign, I get a value back. It's the addition procedure. Okay? So two different languages. Up here, we have variables. We have, for example, here's exp is a variable. So even though the calculator language doesn't have any variables in it, you know, if I type exp into the calculator program, error, bad expression. But I can type exp into STK, and well, if I do it right now, I get an error message also because the variable is local to calceval. But I can say calceval, that's a variable, and its value is a procedure. All right? So two different languages, two different prompts. There's the STK prompt, which looks like that, and then there's the calc prompt, which looks like this. Okay? These languages are different enough that I don't think any of you is going to get confused about this point. So we can't write, for example, an if expression or a cond expression in calc language, but we can use cond, as we do up on the screen here, in Scheme in defining what the calculator language is. Okay? I'm belaboring this probably obvious point because pretty soon we're going to be looking at Scheme interpreters written in Scheme. And that's going to make it a little more confusing. So I want you to get this point clear in your head while the languages look pretty different from each other, that when you have a Scheme interpreter in Scheme, there are two languages involved. There's STK scheme, and there's my scheme interpreter scheme, right? And they're going to be a little bit different from each other. So we didn't implement every single feature of real scheme in our interpreters. We just took, the ones we thought were important. And so the languages are different, but they look very, very, very similar. And so if we allow, for example, conned expressions in our scheme interpreter, and if the procedure that implements conned expressions uses a conned, many of you are going to think the first time you see that, oh, wait, this is cheating. Right? How can you use conned to define conned? And the answer is we're not cheating at all. We're using STK conned to define our interpreter conned. Okay? So try and keep that straight while it's simple as preparation for the next big step. Another thing about eval and apply, and this is why I brought up syntax versus semantics. Eval lives in both of these worlds. In a sense, eval is the program that turns the syntax into the semantics. It knows the form of a program that you type, and it turns that form into something meaningful that's a request to compute some value. Okay? So it takes an expression, a piece of syntax, as argument and returns a value. Apply doesn't know anything about syntax. And this is why apply is separate, a whole separate thing from eval when we think about it. Because the two arguments to apply in the real interpreter are a procedure and argument values. So it's not the notation for a procedure. It's not like lambda blah, blah, blah. It's a procedure and values that it takes. So it's all in the world of values. Its work is entirely about semantics and not about syntax. So any piece of syntax that's in the language is going to be taken care of by eval, except for, I should say, the pieces of syntax that are handled by read, which is mainly the parentheses, but also quotation marks. Okay? Oh yeah, one last thing. Okay. Yeah, it isn't true here. Eval calls apply right here. Right? When we get to an actual scheme apply, we're going to see that apply calls eval. Think for a moment about why that's true. Back to scheme now. What does it mean to call a procedure? It means compute the actual argument values, substitute the actual argument values for the formal parameters in the body, right? And then evaluate the resulting expression. So when you call a procedure, eval is going to end up calling apply. So this is eval and apply calling each other back and forth. And that's a pretty complicated control flow. If you try to draw one of those diagrams like they did for Fibonacci numbers with trees and arrows going up and down and everything, it gets pretty complicated. And it needs to be complicated because of the complexity of deep lists as a form of expression. Right? So when you have a list of lists of lists of lists, and so each of those, so what that is a function call that involves function calls to compute the arguments, and those things involve more function calls, and so on. You need this thing that's called mutual recursion to handle it. Mutual recursion is going to be a big part of what we look at next week when we talk about trees as a data type. So I wanted to leave you with this sort of preview of coming attractions. And we'll see it in the scheme interpreter at the end of next week. Any last questions? once? Ah, yes. Wait, hang on, stop. Okay, syntax and semantics. Okay. His question, and it's a good question, so don't be in a hurry to leave, is why doesn't apply care about syntax? Because syntax is important in function calls just like semantics is. So here's why. Okay, here's a scheme function call. Here's the same thing in almost every other programming language, right? Right? Here's another procedure call, function call, f of 3 and 4. And in almost any other programming language, it's f parenthesis 3 comma 4 close parenthesis. Okay? Does apply know which of these things you typed? No. Apply knows that you want to call the function f, and you want its argument values to be 3 and 4. Okay, that's what we tell apply. Getting from this string of characters, open paren f space 3 space 4 close paren, or f paren 3 comma 4 close paren, getting from that to the arguments to apply is eval's job. So eval takes this semantic stuff and gets rid of it. So we're left, I'm sorry, this syntactic stuff and gets rid of it. So we're left with the semantics of calling a function. Does that answer the question? Okay, great.